You steered it in this morning without thinking. Milk into coffee. A quick swirl, and for half a second before it all went brown, you saw it. Those little curls folding into smaller ones still. Chaos. Gone in an instant. That swirl is a $1 million problem. Not a joke. There's a literal price. $1 million. For anyone who can truly explain what your spoon just did. And no one has claimed it. The smartest mathematicians alive have tried it for over 100 years. They wrote down the exact equations. They have the equations, and they still can't solve them. Now, look up. 93 million miles away, the surface of the sun is about 5,500 degrees hot. But go higher, up into the thin air above the surface, and instead of cooling down like it should, the temperature jumps to over 1,000,000 degrees, 200 times hotter, further from the fire, and somehow hotter. It's like walking away from a campfire and feeling the heat get stronger. Nobody knows why. Two problems. One in your coffee cup, one on a star. Both look almost simple. Both have humiliated physics for decades. And weirdly, they might be two faces of the same monster. Let me show you the two simplest problems no one can solve. Okay, toddler version. Water flows. You know this. Rivers flow, taps flow, blood flows. It's the most ordinary thing in the world. Surely, we understand water. Here's how sure we were. Back in the 1800s, two scientists, a Frenchman named Navier and an Irishman named Stokes, sat down and wrote the rules for how any fluid moves. Water, air, honey, smoke, anything that flows. They boiled it all down into a set of equations, the Navier-Stokes equations. And these equations are good. They are not a rough guess. Engineers use them to design airplane wings, weather forecast, race cars, blood flow in your arteries. They work. When you flush a toilet, when a plane doesn't fall out of the sky, these equations are quietly running underneath. So we're done, right? We have the rulebook for all flowing things. Here's the twist that should not be possible. We have the equations. We cannot solve them. Let me say what that actually means, because it sounds insane. Having an equation isn't the same as being able to work out what it does. Imagine a recipe written in perfect detail, every ingredient, every step, but no one on earth can actually cook it. That's where we are with water. For the smooth, gentle case, slow water, a lazy stream, we can just about manage. But the moment the flow gets fast or messy or wild, the moment it becomes turbulent, the equations turn into a nightmare no one can crack. And here's the thing, we can't even prove something incredibly basic.
We can't prove that the equations always give a sensible answer. For all we know, somewhere in the math, a perfectly normal looking flow could blow up to infinite speed out of nowhere.
And nobody has been able to prove that can't happen. 150 years after we wrote them down, we can't even guarantee the equations behave. That's why in the year 2000, the Clay Mathematicians Institute put it on a list. 7 problems. The hardest, most important, unsolved problems in all of mathematics. Solve one, get $1 million. Navier-Stokes, the equations of water, is on that list, sitting right next to the deepest puzzles humans have ever posed. The prize is still unclaimed. So what's the actual villain here? One word. Turbulence. Turbulence is what happens when a flow stops being smooth and starts being chaotic. The curls in your coffee, the wobble of rising smoke, the bumps that rattle your plane, the churning white water of rapid. And here's what makes it a monster. Turbulence is a chaos inside a chaos. A big swirl breaks into smaller swirls, which break into smaller swirls, which break into smaller ones still. Energy cascading down through every size at once, all tangled together, feeding back on itself. Every part affects every other part. You can't isolate one piece. You can't zoom in and simplify. It's all connected, all the way down. The great physicist Richard Feynman, one of the sharpest minds of the last century, called turbulence the most important unsolved problem of classical physics. He also supposedly said that if he could ask God one question, it might be, what is turbulence and why? There's a line that gets passed around physics that captures how upside down this is. We understand the inside of an atom, the strange, ghostly quantum world, better than we understand water pouring out of a tap. The exotic, faraway stuff, we've got a handle on it. The everyday stuff, the water in your glass, still a mystery. You use turbulence every day. You've never once needed to understand it. And neither has anyone else, because we can't. And this isn't just mathematics being fuzzy. If we truly crack turbulence, we could design planes that sip fuel instead of guzzling it. We could predict the weather much further out, because the atmosphere is one giant turbulence fluid. We could understand blood flow, ocean currents, the spread of pollution, even how galaxies form. Turbulence is everywhere, and everywhere is exactly the problem. It's too common to ignore and too complex to solve. Hold that idea. Chaos cascading through every scale at once. Because now we leave your kitchen and go to the sun, and we're going to meet it again. Everything you know about heat says the next thing is impossible. Heat flows from hot to cold, always. Your coffee gets cold. It never steals heat from the room to warm itself back up. Stand near a fire, and the closer you get, the warmer you feel. Step away, and you cool down. This is the most reliable rule in all of physics. Heat moves from hot things to cold things, and never the other way. It's basically a law. Now, the sun. At the core, it's a furnace, millions of degrees, where nuclear fusion crushes hydrogen into helium and lights the whole thing up. That heat pushes outwards, and by the time it reaches the surface, the part you can actually see, called the photosphere, it has cooled to about 5,500 degrees. That makes sense. Further from the furnace, cooler, just like stepping back from a fire. So keep going, go up off the surface into the sun's thin outer atmosphere, the corona, the faint glow you can only see during a total eclipse. You're now even further from the core. By every rule you know, it should be even colder up here. It's over 1,000,000 degrees. Not a little hotter, 200 times hotter than the surface right below it. You walked away from the furnace and the temperature exploded. Let that sink in. Because it breaks the one rule heat is never supposed to break. Picture a campfire. You step back expecting to cool off, and instead the air gets hotter. You step back again, hotter still. The empty space away from the flames is hundreds of times hotter than the flames themselves. That's the sun. The surface is cool. The near empty atmosphere above its furnace. And here's a thin layer between them, just a couple of 100 kilometers thick, where the temperature doesn't gently rise. It rockets from thousands of degrees to 1,000,000, almost like flipping a switch. Heat is flowing, in effect, from the cooler surface to the hotter atmosphere above, from cold to hot, the wrong way, the impossible way. This is called the coronal heating problem, and it has been staring physicists in the face since 1939, when scientists first realized the corona wasn't just glowing, it was scorching, far hotter than anything below it. Nearly a century later, there is still no settled answer. Now, the universe isn't actually breaking its own rules. Heat can't spontaneously flow uphill. So the honest version is this: something must be carrying energy up there and dumping it. Some hidden delivery system that pumps energy into the corona and heats it from within. Not conduction, not the heat simply spreading from the surface. Something else, something active is doing the work. The energy has to come from below. Everyone agrees on that. The churning surface of the sun is a violent, bowling, magnetic mess, and it holds enormous energy. The question, the whole mystery, is how that energy gets up into the corona and released. And this is where, after almost 100 years, we still only have suspects. Not a verdict. Suspect number 1. Magnetic waves. The sun's surface is boiling and twitching constantly, and it's threaded through with powerful magnetic field lines, like invisible guitar strings running up into the atmosphere. When the surface churns, it plucks those strings. Waves race up the magnetic field lines into the corona and break there, dumping their energy as heat. Ocean waves crashing on a beach. Except the beach is 1,000,000 degrees. Suspect number 2. Nano flares. You've heard the solar flares, those giant explosions that fling energy across space. Now imagine tiny versions, billions of them, popping off constantly across the whole surface. Each one microscopic on the sun's scale, but together an unrelenting barrage of little detonations, each dumping a spark of heat into the corona. Not a big blast, 1,000,000,000,000 tiny ones. Both ideas are good, both have evidence, both have problems. And the frustrating, honest truth is that the answer is probably some mix of both, with the balance changing from place to place, and no one able to nail down exactly how much of each or exactly how it all adds up to 1,000,000 degrees and stays there. We have sent spacecraft to fly through corona to find out. We are literally touching the sun to solve this, and it's still open. Now, here's the part I find it beautiful. Go back to your coffee. Remember what made turbulence impossible. Chaos cascading through every scale at once. Energy tumbling from big swirls into smaller swirls all the way down. Everything tangled, everything feeding back on itself. Impossible to pin down. This is exactly what's happening on the sun. The surface of the sun is a turbulent fluid, a churning, magnetic, boiling ocean of plasma. The waves, the nanoflares, the twisting magnetic field, they are all born out of the same untamable chaos. To fully solve why the corona is so hot, you'd have to understand how energy moves through a wild, turbulent, magneticized fluid across every scale at once. Which is the first problem? The coffee cup problem, the one we already can't solve. So two mysteries aren't really separate. The fire in the sky is the swirl in your cup, just 100,000,000 times bigger, 100,000,000 degrees hotter, and wrapped in magnetism. The same monster, two faces. Turbulence is the thread running through both, and turbulence is the thing we've been stuck on for 150 years. So let me leave you with this. We can fly a spacecraft to the edge of the solar system with pinpoint accuracy. We can find the Higgs boson. We can detect two black holes colliding 1,000,000,000 light years away from the tiniest tremor in space itself. And we cannot tell you from first principles what your spoon did to your coffee this morning, or why the air above a star is hotter than the star. That's not a gap in the fancy, faraway physics. That's a gap in the ordinary stuff. The water in your glass, the warmth of the sun on your face. The two most common things in your life. Flowing fluid and heat. And at the deepest level, we can't fully explain either one. Maybe that's the lesson. We reach for exotic, quantum black holes, the edge of the universe. And we assume the simple things behind us are already solved. They're not. Some of the biggest unsolved problems in all of physics aren't hiding at the edge of reality. They are in your kitchen and in the sky, hiding in plain sight. In the most ordinary moment, waiting quietly for someone to finally understand them. Maybe that someone is watching this right now. Stir your coffee. Look at the swirl. Nobody on earth can explain it. Isn't that wonderful? God bless you.